Alright, so in a previous video, we showed how time is what gives compound interest its snowballing effect of exponential growth. So what if we were to make compound interest even more powerful by adding regular contributions to our investments? And this is the idea behind what we call in Australia superannuation, or more generally, annuities. Or another name for it would be pension funds, which is the idea of making regular payments at regular intervals with the added power of compound interest to accumulate a large lump sum payment at the end, as for example, like a retirement fund payout. In this video, we're going to develop a simple model to demonstrate the power of superannuation for ordinary annuities. We're going to be keeping things quite general. So let's say a pension fund pays a yearly interest rate of I, and of course that's normally expressed as a percentage. It's paid yearly, and we're going to be making regular payments yearly. And I should say at the start of each year. So let's draw a timeline. We're going to start making payments at the start of year 0, so let's mark that. And we're going to calculate the amount that is due at the end of year, let's say year 20. And to keep things really simple, we're just going to be making payments of $1. Alright, so at the start of year 0, we'll make our first contribution. Let's call this C1 of $1. This $1 is going to accumulate interest for the entire period. So at the end of 20 years, the amount accumulated for this $1 invested, let's call this A1, the accumulated amount, will be, according to the compound interest formula, it's P by 1 plus the interest rate to the power of the number of payments N. The number of payments is 20. After 20 years, the principal is just $1. And because 1 times anything is itself, to keep things simple, I'm just going to erase this $1 at the front of that expression. So A1, the amount accumulated for our first investment after 20 years is 1 plus I to the power of 20. Now, after 1 year, we're going to make another contribution because, as we said at the start, the idea is to make regular payments at regular intervals. The second contribution, let's call it C2, we make after 1 year. So it's another $1 invested, but this time it's only going to be accumulating interest for 19 years. So A2 will be the $1 by 1 plus the interest rate to the power of how many payments, and it's going to be 19 because we'll make the payment at the start of year 2. So it's going to accumulate interest for the remainder of the term, which is 19 years. And to keep things simple, I'm going to erase this $1 at the front. After 2 years, we're going to make another contribution. Let's call this C3. So at the beginning of year 3, or after 2 years, we make another $1 investment. So for the remainder of the annuity, that contribution is going to accumulate interest for 18 years. So the accumulated amount of contribution number 3, A3, is going to be $1 times 1 plus I to the power of 18. Again, for simplicity, we'll erase this $1 at the front. So hopefully you can see a pattern emerging now. We'll make our final contribution at the start of year 20. The 20th contribution will be made after 19 years at the start of year 20. And this is only going to accumulate interest for 1 year. So A20 will simply be equal to the $1 invested. So the $1 invested here by 1 plus I, because that particular contribution only has 1 year to grow. So the total amount accumulated in this pension fund that's due for payment at the end will simply be the addition of all of these accumulated amounts. So it'll be A1 plus A2 plus A3 all the way to plus A20. So let's write this as S sub 20 the amount accumulated in this pension fund at the end of 20 years will be A1 plus A2 plus A3 plus so on and so forth until A20. And we can write this out as 1 plus I to the power of 20 plus 1 plus I to the power of 19 plus 1 plus I to the power of 18 plus dot 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 plus 1 plus I. And now for convenience, I'm going to write this expression in reverse. So I'll write this as 1 plus I plus 1 plus I squared plus 1 plus I cubed plus all the way to 1 plus I to the power of 20. And now I'm going to write it like this: 1 plus I plus 1 plus I by 1 plus I plus 1 plus I by 1 plus I squared plus 1 plus I by 1 plus I cubed plus dot 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 plus 1 plus I by 1 plus I to the power of 19. And the reason why I did this is because, can you see here that we have a geometric series with A equals 1 plus I, R, the common ratio, is equal to also 1 plus I, which is this guy here. So the sum of a geometric series to the nth term, this is given by the formula S sub n is equal to A by R to the power of n minus 1 all over R minus 1 when R is greater than 1. Alright, so unless we have a negative interest rate, which I hope you'll never encounter, R is always going to be greater than 1. So for our particular case, we've got S sub 20, the amount due after 20 years, is equal to 1 plus I by 1 plus I to the power of 20 minus 1 all over 1 plus I minus 1. The denominator we can simply simplify to I. Okay, so this is after 20 years. What if the pension fund offers us a term that's longer than 20 years? Well, most people would be working for more than 20 years of their life, and so would be contributing to their retirement for more than 20 years. So that's not a problem, because more generally, instead of writing 20, we can just write n for any number of years for the annuity. Okay, so this formula has been developed for contributions of $1 only. And I said at the beginning we did that to keep things simple. So what if we're making yearly contributions of, say, $10? Well, the good thing about getting this formula for $1 is that when we make contributions of $10, we've just got 10 of $1 doing the same thing. So we simply multiply S of n by 10. So we've got $10 times S of n to calculate the amount after n years for contributions of $10. Similarly, if we raise that to $100, we simply multiply S sub n by $100. So if I generalize that now for yearly contributions of, say, C dollars, then the amount due after n years, let's call this D sub n, it will simply just be C times S sub n. So expanding that, we would have the amount due of a pension fund at maturity is D sub n, D after how many years, is equal to the regular contributions times 1 plus I, the interest rate, outside of 1 plus I to the power of n minus 1 all over the interest rate I. So let's box this and keep the formula handy for future reference. So we'll do some examples in upcoming videos, but we'll leave it here for now. Thanks for watching. If you have any questions, write them in the comments below and I'll do my best to answer them. If you found this video useful, please share it with your classmates, like it, check out my channel for hundreds of other videos to help you with your math studies, subscribe, and best of luck with your studies.